So I am fully optimistic we will see a gradually cooling trend in most of the time of this century. My name is Qing-Bin Lu, and I'm the professor in the Department of Physics and Astronomy, University of Waterloo. I started interested in environment science since the late 1990s. And then at the beginning, I focused on the ozone depletion research. So about 10 years later, 2008 to 2009, I started interested in investigating on the subject of the climate change. So in today's presentation, I will talk about my theoretical and the observation results from this list of publications. Especially will be more from the recently two papers, 2022 and 23 papers. In 2022 paper, I presented quite a comprehensive observation data sets to show that the climate change, especially the global warming since the late last century, are caused mainly by the CFC instead of CO2. And then in the 2003 paper, I give the critical review on the radiative forcing and the climate models, including the conventional, the GCM, the general circulation model, and my own model for climate change. And I focused the review data since 1970s. So that's the 2023 paper. Okay, so let's start from the review about the Nobel Prize in Physics in 21st. So as you can see that these three scientists was awarded a prize for 2020 first in physics. This citation is that for their groundbreaking contribution to our understanding of the compressed systems. And one of the prize went to Dr. Shukla Manabi and Klaus Hasselmann for the physical modeling of the Earth's climate and the quantify vulnerabilities and reliably predicting global warming. So I hope in this slide you will see how reliably they predict the global warming. Let's start to review the popular science background document given by the Royal Swedish Academy of Science. So it decided that say that Manabi and Hasselmann are awarded a prize for their pioneer work on developing climate model. Shukla Manabi demonstrated how increased concentration of carbon dioxide in the atmosphere, leading to increased temperature at the surface of the Earth. In the 1960s, he led development of a physical model of the Earth's climate and was the first person to explore the interaction between radiation balance and the particle transport of air masses. His work laid the foundation for the developing of climate model. And then about 10 years later, Klaus Hasselmann created a model that linked together weather and climate and answering the question why climate models can be reliable despite the weather being changeable and chaotic. He also developed a method for identifying specific signal, fingerprints that both nature phenomena and human activity imprinted in the climate. His method has been used to prove that the increased temperature in the atmosphere is due to human emission of carbon dioxide. So based on this statement, we can see that this pair are awarded a prize because they are developing CO2-based climate model, right? Because here, obviously, they mentioned in both paragraphs, they mentioned CO2, the carbon dioxide. This slide was also given by the Royal Swedish Academy of Science. So this slide is to illustrate that when the CO2 concentration increases in the atmosphere, the temperature in the lower atmosphere, we call this troposphere, below 10 km from the ground to the surface, the temperature will increase when CO2 concentration increase. By contrast, in the upper atmosphere, this so-called stratosphere, and you can see that they shows that when the CO2 concentration increase, the temperature will decrease. So this so-called stratospheric cooling. And this graph shows that when the CO2 concentration increased from 150 ppm to 300 ppm, the surface temperature will increase between 2 to 3 degrees. And then the temperature in the stratosphere will be decreased by about 10 degrees. So when they increase to 300 to 60, similarly, the surface temperature will increase between 2 and 3 degrees. And then the temperature in the stratosphere will be decreased by about 10 degrees. Actually, this graph originates from Dr. Manabi and Wessler's paper published in 1967. So that is their model prediction. So here I ask, what is the truth? What is the real observation we have seen? And that's what I'm going to present you in the later slide. We can also see, let me move this. We can also see this is the last concluding paragraph for this, the popular science background document given by the Royal Society of Swedish Academy of Science. Okay. So it is said that Shukla Manabi and Klaus Hasselmann have contributed to greatest benefit for humankind in the spirit of Alfred Nobel by providing a solid physical foundation for our knowledge of Earth's climate. We can no longer say that we didn't know the climate model are equivocal. That means incontrovertible. Okay. Is Earth heating up? Yes. Is it the cause of increased amount of greenhouse gas in the atmosphere? Yes. Can this be explained solely by nature factor? No. Are human emissions a reason for increasing temperature? Yes. So based on this the concluding paragraph, to discuss for the contribution of these two laureates, okay, and you can see that the Royal Swedish Academy of Science, they didn't ask and didn't answer what is the major greenhouse gas cause the warming. They didn't say that. And this paragraph is following with this figure, okay, that they stay together, okay. In this figure, the title is identifying the fingerprint in the climate. So basically, they say that Dr. Hasselmann developed a method for distinguishing between nature and human cause, the so-called fingerprint of atmospherical heating, the warming. Okay. In the figure, you can see that this the black curve that is observation. The blue curve that is calculation shows the effect of nature effect, that including solar effect and volcanic effect. Okay. The red curve, there is the calculation based on the climate model. Okay, they including both nature and human effect. So here you can see this larger dip, and that's correspond to the well-known larger volcanic eruption. So here is a larger dip. In this document, they cited this on this reference. In fact, the original this figures came from IPCC AR4. So if you read AR4, you will see this figure. Okay. So the main point is that actually in last slide, they say these two laureates made a contribution for CO2-based climate model. Right? But in this concluding paragraph, they didn't identify CO2 at all. They didn't talk anything about CO2. And this so-called identified fingerprint of the climate changer, again, here you don't see anything about CO2. They didn't tell you what is the major greenhouse gas. So to me, it's quite strange. This is inconsistent with what we have seen in the last slide, right, in the statement. The lawyers, the Swedish Academy of Science, they also give another document, so-called scientific background document, for the prize presentation. Okay, and in this scientific background document, in section 4, it's using observation to test the model. A, fingerprinting. If you read this title, you will expect they will take what is the key observation to demonstrate that, this CO2 make the global warming. Okay? We will expect that. But if you read this document, the whole document, in this whole paragraph, okay, you didn't see they mention anything about CO2. This whole paragraph actually is basically describe how Dr. Harshman developed his method to distinguish the nature and human effect of climate change. And they didn't mention at all about CO2 in that whole paragraph. And this is the last paragraph for the contribution of this Dr. Malabi and Harshman to the climate science. This is the last paragraph. It says that Harshman's paper was a statistical roadmap for hundreds of subsequent climate change detection and attribution studies, and provide strong scientific support for the conclusion reached in IPCC AR5 that was published in 2013. And it cited that it is extremely likely human influence has been the dominant cause of observed warming since the mid of 20th century. So again, you can see here, they didn't mention which greenhouse gas is the dominant cause of observed warming since the mid of 20th century. So I don't know how you relate this, the CO2 climate model, okay, to attribute this, the contribution of these two areas, right? But either in the popular science background or this scientific background, in the concluding part, you didn't see they identify which greenhouse gas is the dominant cause of the observed warming since late 20th century. The one co-recipient of the Nobel Prize in Physics in 1973, Dr. Eber, okay. He gave a very famous talk in the 62 Linde Nobel Laureate meeting. And the title of his talk is The Strange Case of Global Warming. This is a very interesting talk. Actually, I watched this video a few times and I love it. Okay. One comments he made, one statement Eber made is that he said that I believe that nothing in science is incontrovertible. Okay. Thus, in my view, the American Physical Society became a political or religious society. Consequently, I resigned from APS in the fall of 2011. Personally, I don't completely agree with every point Dr. Eber made about the global warming or climate change. Okay. However, I do agree with his comments. Okay. In science, nothing is incontrovertible. Otherwise, we would not have the relativity theories or the quantum theories that was developed in last century. Right? So in science, nothing is incontrovertible. Nothing is indisputable. Okay. Otherwise, science would not be advanced. So I tend to agree with what the comments he made about the nature of science. Okay. And I feel very strange to see that the lower Swedish Academy of Science say that the climate model are incontrovertible. Okay. I feel very strange to see that kind of comments. Okay, so now I want to review what is the observation we have seen. Okay, earlier we showed this graphic from the lower Swedish Academy presentation. Okay, so this shows that the climate change since the late last century, since essentially from 1970 or 1975, is mainly caused by human effect. For these results, this quite similar to what I presented in my 2013 International Journal of Modern Physics paper, although in my book. This figure came from my book. And as you can see that this look very similar to each other. But the approach is different. I didn't took Dr. Harshman's method in the model he developed. basically my approach is observation-based approach. Okay, so I study the multiple observation data set from the total solar irradiance up to sunspot number to cosmic ray, because as you know that the cosmic ray intensity is correlated with the solar intensity. Okay, so that based on ID mu, the multiple data set, it seems quite robust that the temperature increase since about 1970s mainly is caused by human effect instead of the nature effect. I'm aware about this. Some scientists argue that the solar effect could contribute to the warming, but based on the data set, multiple data set ID mu, actually in the solar cycle since the 1970s, there were cause decreasing of that we have the cooling trend instead of the warming trend, and that not only from the total solar irradiance. Okay, actually, you look at the cosmic ray, because the cosmic ray intensity anti-correlated with the solar intensity, and you can see that in the past few solar cycle, the cosmic ray had the increased trend. So that's correspond to the decreased trend in the TSI. Okay, and so based on that, the warming we have seen in the last century cannot be caused of the nature effect. So this is consistent with the conclusion they reached in the conventional based on this the method developed by Dr. Hasselman. So I don't have disagreement with this conclusion. And then one major prediction we have to carefully make is the GCM model developed by Manabi and Gradual in 1975, the GCM. This is one of the two major papers cited by the Lower Society Academy, lowest Swedish Academy of Science for the contribution of Dr. Manabi. Okay, and the earlier one I mentioned is 1967. This one is published in 1975. So this graphic came from this paper. Okay, so as you can see that they discussed that when CO2 concentration double, okay, in the atmosphere, and you can see they were making a warming in the troposphere, okay, in the lower atmosphere from 0 to 10 km. And near the top, the temperature will increase between 2 to 3 degrees, as we have seen earlier, okay, in the earlier graph. And then in the high latitude area, that means in the Antarctica and the Arctic, okay, and you can see that the temperature they predict that will increase by 7 to 10 Kelvin. Okay. So this is much larger warming than the warming over the tropical region, right? As you can see from here. This one very important. Okay, even in this paper they point out that the number might not exactly accurate. However, they do including this the presentation by the Lower Swedish Academy of Science. They do point out that they predict that the temperature increased by 2 to 3 degrees by the CO2 doubling, right? Okay. So the number doesn't matter, of course. This number, okay, to matter, right, is important. Okay. So here they predict 7 to 10 Kelvin if the CO2 concentration is doubling. So we have to see what has been observed in real observation, because this will tell us how reliable this GCM, the CO2 GCM model, how reliable they predict global warming. So I will show you that really observation in the later slide. This is another prediction based on Dr. Manabi's modeling results on the temperature increase. This paper was published in Nature in 1978, and they discuss based on that the Manabi's GCM model, they predict the temperature will increase 7 to 10 Kelvin over the high latitude area. Okay, and this for that 8 degrees south. That means Antarctica, right? And based on that temperature, 7 to 10 Kelvin increase, And they found that, they predict that there will have the rapid deglaciations of the West Antarctica. And they were leading to an increase of sea level of 5 meters if CO2 level is double in 50 years. So from 1978, that 50 years will be 2028. So will be 5 years more from now. And they predict we will see 5 meters rise in the sea level. Let's look at what is the observation. Okay, so this observation shows that between 1901 to 2018, the average global sea level increase is by 15 to 25 centimeters only. Okay, so that's drastically, orders different from 5 meters rise in the sea level. Of course, we have not yet double CO2 level, right? But you can expect that if this prediction is true, we see a fewer meters rise in the sea level. And by contrast, we observe about just up to 25 centimeters, 0.25 meters. So that is, is orders difference from the prediction by this GCM. Okay, so let me review one of the central physics concepts in the climate model, including GCM, and that is radiative forcing. Okay, so the RF. Okay, so this forcing defines the initial radiative flux imbalance at the top of the atmosphere, as the Earth's climate system is imposed by the small energy perturbation. And that could be an increase of the greenhouse gas concentration or the change of the income solar radiation. So basically, you can express that the forcing is equal to the income solar radiation flux minus the outgoing radiation flux. And this is measured in the top of the atmosphere. Okay, before the surface temperature change. Okay, so this is the so-called instantaneous RF. Okay. In climate model, the radial forcing, okay, RF, actually also called this the SAF, okay, is computed in terms of the radiative perturbation at the tropical poles instead of top atmosphere. After the stratospheric temperature has been allowed to adjust to radiative equilibrium, where the surface and the tropical temperature and state variables such as the water vapor and the cloud coverage are fixed at the initial unperturbed values. Okay, so they allow the temperature in the stratosphere to change. So this we call this the SAF. Okay, the stratospherically adjusted radiative forcing. So they allow the temperature in the stratosphere to adjust to build the new equilibrium. Okay, so that is called this the RF. Okay, since 2013 IPCC AR5, another term has been introduced, and it's so-called effective radiative forcing (ERF). The ERF is defined as the change in the net downwards radiative flux at the top atmosphere up to now the stratospheric temperature and tropospheric temperature, water vapor, and clouds just to keeping the surface temperature or the partial of the surface conditions, such as the sea surface temperature, unchanged. Okay, so that's slightly different from the definition of the SAF. However, in the fifth or the sixth generation of the GCM, the CMIP5 or CMIP6, actually there's very little, almost no difference between RF and ERF values for where mixed greenhouse gas, as I will show you next slide. So even the definition is slightly different, the value, the difference actually is quite small. Simplified analytical formulation, okay, has been derived from the atmospheric radial transport model, okay, and those simplified analytical formula of RF are often used to calculate the radiative forcing for where mixed greenhouse gas, and that including the CO2, the CH4 or the N2O, and also halogen greenhouse gas. Okay. So for halogen greenhouse gas, there is very simple linear dependence between the radiative force and the concentration of the halogen greenhouse gas. Here, this parameter, this constant, chi, that is specific for each greenhouse gas, depend on their absorption intensity in the atmospheric window. For CO2, this radiative force can be simplified, expressed as this is equal to 5.35 times logarithm C divided by C0. C0 is the concentration before industry revolution, so approximately 278 ppm. And C is the current carbon dioxide concentration. Here again, they have this logarithm relationship between the force and the CO2 concentration. So the reason they use this logarithm function is they consider the partial saturation, not complete, partial saturation for the CO2 infrared absorption in the atmosphere. Okay, I will explain more detail in the later slide. They consider that partial saturation, not complete saturation of the CO2 infrared absorption in the atmospheric window, not in the atmosphere. So if you compare the RF value calculated by this simple relationship with the so-called high spectral resolution radiative transport calculation in GCM, okay, and actually the agreement is excellent. It's within 5%. Okay, it's almost perfect. Okay, as you can see, I chose here. If you look at the ER value, and the value is just simple calculated by this two equation. Okay, for CO2, if you check the ER value given by IPCC AR5 and this equation. Okay, so you see this open circle here. That's the data from AR5, all just simple calculate by this equation 3. There is no difference between AR5 and equation 3. It's perfect, the same, identical. And if you compare the value that given by IPCC AR6, the difference also very small. And basically the increase is about 4% only. Okay. So in other words, when they use this equation, actually there's no major difference from you given by the GCM, okay, the general saturation model. For hydrogen gas, there's no any difference. When you use this simple equation 2, all you get to the EF value from AR5 or AR6. They are identical. Okay. These two equations basically give you the same radiative force number they get from GCM. Okay. So here, the key question is that what is the major substance is made in those equations? Okay, especially for CO2. So this including this equation, or in this so-called is the model trend for radioactive transport modeling. Okay, all in GCM. What is the major substance made there? Basically, assuming this logarithm relationship for the force depend on the concentration. Okay, so what is the major substance? Obviously, this is not based on directly observation. This is a substance. Okay, and this substance actually is quite important because this determines what's the scale of the force you have created by increasing the CO2 concentration. So we will later, okay, I will show the 6 key observations to test this relationship. Before that, let's continue to review the climate model. Okay. So one of the important parameters that is climate sensitivity. Okay, and this is to give them the relationship between the surface temperature change and the heat trap in the atmosphere. Okay. So the climate sensitivity factor alpha is defined as a ratio of the response change in the Earth's surface temperature to a force created because the infrared radiation trapped in the atmosphere by greenhouse gas, all because change of the solar radiation. Okay. So the ratio, okay, this is called the climate sensitivity factor alpha. This is also called reference climate sensitivity or the Planck feedback factor, okay, because this is from the directly response in surface temperature to a force, and this is not including any feedback factors. Okay. Of course, the equilibrium surface temperature change, okay, must also consider the climate feedback factor. When the surface gets warmer, they try to pump more water vapor into atmosphere. So we have to consider the feedback factor, water vapor, the lapse rate, the elevator, and the crowd cup change, right, etc. And all of that could, amplify the prompt response, the direct response to a change in the force, radiative force, right? So then the equilibrium surface temperature can be expressed as beta times alpha times the radiative force, right? And you can write this as a lambda c. So here lambda c will be called this equilibrium climate sensitive factor. Okay. And this beta, okay, you can call this the total amplification factor. Okay. In IPCC AR5, they give the beta number, okay, is approximately 3.3 with a larger range 1.7 to 5. And in AR6, okay, they given the beta value is approximately 2.8, again with a larger range 1.9 to 5.9. So you see, this value is it's a bigger uncertainty. And it's generally believed that this large uncertainty arising from uncertainty in the feedback factor of wet vapor and the cross. Okay. So when this beta larger uncertainty, of course, this lambda c, okay, the equilibrium climate sensitivity factor will also have larger uncertainty. And when this uncertainty, of course, the temperature simulated by the model, the climate model, will also have a large uncertainty. So this is very obvious, right? In AR3 or AR4 IPCC report, they keep this separate terms, alpha and beta. However, in AR5, AR6, they no longer separate terms of alpha, beta. Even they mention about this beta value, okay? Instead, the equilibrium climate sensitivity factor lambda is given with this in reverse relationship to the total feedback parameter. This eta, okay? And this eta is the sum of the Planck, water vapor, lapse, crowd, and the surface elevator feedback parameters. Okay, so they give this inverse relationship. They didn't separate the terms of alpha and beta in AR5, AR6. Okay, but they're essentially the same. That's essentially the same as the AR3, AR4. In AR3, AR4, you can see clear what is alpha value, what is beta value. And in AR5, AR6, you not see obviously. Of course, when they don't give you the specific number, okay, because keep in mind that in GCM, in IPCC climate model, all of this parameter is adjustable because they want to get the best match with observation. So all of those parameters are adjustable parameter. It's not based on the observation. It's adjustable parameter in order to match with observation. So you have to keep in mind that in GCM, the climate sensitivity factor are adjustable parameter. In CO2-based climate model or IPCC climate model, climate sensitivity is often expressed as the so-called equilibrium climate sensitivity, ECS. And this is specifically defined as the temperature increase due to the doubling of the CO2 concentration. Okay, so this when the CO2 concentration is doubled, okay, the increase of the temperature the value that is called ECS. Okay, in AR6, the current model gives the best estimated value of ECS to be 3 degrees, okay, and with a range 2.5 to 4 degrees. This 3 degrees, the best estimated ECS value, actually is identical to the value they give in AR4, and it's almost the same as the value they give in AR5. However, it's also well known that the ECS value changes largely among climate models, okay, and it's also sensitive to the model parameters. Okay, the ECS is not well constrained by observation. Okay, actually, estimated from the modern climate condition give the huge range of ECS within 0.1 to 10 degrees. So the range for the ECS is huge. Okay. In the literature, when researchers give the review about the GCM, okay, this is the atmosphere, ozone cup GCM is advanced level model of GCM. Okay. So when they review multiple GCM and they get the average value for the doubling of CO2 concentration, the radiative force in the case is 3.7 watts per square meter. Okay, they from average from the, in this literature, from 12 IPCC AR4 AOGCM. Okay, the average value for this force, okay, is 3.7 when CO2 concentration double. And the equilibrium climate sensitive factor is 0.79. The ECS, that is the temperature increase when the CO2 concentration double, is 3.1. And if you're doing the simple calculation based on the equation I give in the last 2 slides, you just calculate the forcing denoting the doubling CO2, so that will be 5.35 times log 2 when the CO2 concentration double. You can easily calculate that the forcing is 3.1. So you see it's perfect, the same as identical to the average value from the multiple of AOGCM. Here they also give 7.31. Okay. And you can also calculate this based on this forcing 3.71. If you use the number, this lambda equal to 0.8 Kelvin per watts per square meter. This number actually was given in the IPCC AR3 and AR7. So use these two numbers, okay, you can easily calculate the surface temperature increase because of the doubling CO2 concentration based on this GCM, will give you the 3 degree increase. Okay, so as I just mentioned that this ECS equals 3 was given in AR6, AR4. So just doing this simple calculation, you get the almost perfect identical value as they given in the AR4, AR6. Right? There's no significant difference, almost the same. Okay, and so basically the equation I introduced in last 2 slides. Okay, you can use this, and even the high school student, you can calculate what they get. Okay, the major results from the GCM. Okay. So if you plot this, the surface temperature changes because of that radial force from the greenhouse gas, and you can see that, okay, this arc is a total radiative force from nature and from the human-made effect. Okay, and you can get this blue curve, and you can see here, okay, is the discrepancy between the model results and observation. Right? So in GCM, in order to make the best agreement with the observation, the global mean surface temperature, okay, they introduce the so-called changing temperature changer, or call this the changing climate response, TCR. Okay, so in this new parameter, okay, actually you introduce the additional parameter, this so-called the ozone heat uptake efficiency, CUP. Okay, and this approximately is equal to 0.69 based on the mu of the 12 AOGCM. Okay, so this is added to that total heat feedback parameter ether. Okay. Then now you can write this the temperature increase have relationship with this linear relationship depend on this the forcing, right? And now this climate sensitivity factor become 0.51 instead of 0.8 in the last slide, right? This become 0.51. Another issue is usually you can apply the lag about 10 years for the surface measure the greenhouse concentration. When you calculate the radial forcing, there's a delay time about 10 years. Okay, and this 10 years is based on the empirical study, the temperature change, because they found that when it's the 10 year, they get the best match. So when you apply the 10 year, that can also slightly improve agreement from this modeling results and observation. So here the data shows in the green curve. And it appears that, okay, this green curve can give you very good agreement with observation. Okay, so that comes from this the simplified GCF model. Okay. Again, here you can see the larger dip. Okay, and that's from the volcanic eruption. This same as earlier shows that the presentation by the lawyer Swedish Academy of Science, the graph, they same in the digit a larger dip. Okay. That's come from the larger volcanic eruption. In the new version, in the AR6, okay, probably you don't see this larger dip because they can tune in that the climate sensitivity effect for volcanic force, the effect. So because all of that parameter, they can change that. So they can make this perfect match, make this dip disappear. Okay, but in AR4, you can see that larger dip as I show later, presented by this the lawyers Swedish Academy of Science. Right? You can see larger dip. Okay, so because they tune in that parameter, so in AR6 you no longer see that larger dip. Okay, but it's there. Okay. So you can see that just based on this simple equation, you can well demonstrate that how this GCM they can predict for this surface temperature change. Right? What's their capability to predict the how reliable they predict the temperature change. In addition to radiative forcing because of the greenhouse gas, we have to also consider the ozone, right? Because ozone itself is a greenhouse gas, and because the ozone in the atmosphere, the concentration can change, especially not only stratosphere, in the troposphere, the ozone concentration also changes because of the air pollution, right? As we well know. And we have to also look at the forcing because of the aerosols. Okay, the aerosol concentration changes, that will also change the radiative force. Right? And these results came from the IPCC AR6. And I think this is very interesting and very important. As you can see here, the red curve, that is the aerosol level, the concentration in the Arctic, okay, over the north high latitude region, Arctic, okay. And you can see that this aerosol level significant increase about from earlier 1990s, and then the peak is 1950s. So after, because we start to control air pollution, so this aerosol level decreased to 2000s to now in this century. You can see that basically the aerosol level has declined to the pre-industry revolution level for Arctic, right? So you can see now we don't have that significant aerosol level for Arctic. Okay. For Antarctic, over South Pole region, that is the curve in the bottom. So basically just flat. So you can see that there's no significant increase in the aerosol level since the industry revolution, okay, for Antarctica over the South Pole region. And the similar results can also look in the black carbon levels. Okay, so basically they get the same results as this. For ozone in the troposphere, we can see that in the lowland hemisphere, there's significant increase in the ozone concentration since 1960 to 2000s. Okay, but over the South Pole region, actually, it's quite clean. The increase of the ozone is very small. Okay, as you can see that. Okay, IPCC6 also give this the EII for ozone and aerosol. So here I brought this the sum of these two type of aerosol. Okay, and for ozone, you can see that this EII is small increase, but then for this aerosol, there's a larger drop, right, from 1850 to 1960. Okay, so this is about 1.5 watts per square meter drop for this air force. It's very large, given by this model. Okay, why they give this? Actually, they have to give this larger model, because if you base on that equation, the force CO2 from 1850 to 1960, that force is quite large. It's about 1.5 watts per square meter. But we know from the observation, the surface temperature have not yet increased larger from 1850 to 1960. It's only increased about 0.2 to 0.3 degree. But that including both the nature effect and the human effect. So if you remove the nature effect, then the human effect just make that increase very small. So in order to offset the larger relative force from CO2, they have to get out the larger aerosol forcing, right, to balance because this aerosol is the negative, right? So this negative forcing must be balanced that larger positive forcing from CO2, because the temperature, surface temperature, not increase significant largely from 1850 to 1960, right? And interested from 70 to 2010, this actually increased very small, almost flat, right? So even when you sum this ozone and aerosol together, from 1970 to 2010, that increase is very small. It's only 0.1 watts per square meter. I have to point out that you cannot take this number too serious, because if you compare the value given by IPCC AR5 and AR6, and you will find that for aerosol, the radiative force, they only change value between 50 to 85%. So even between AR5 and AR6, the ER value given by IPCC report for aerosol the change is between 50% to 85%. So there's huge uncertainty. So you shouldn't take this too serious, because the uncertainty is so large. So how you know, with the 7-8 year difference between AR5 and AR6, they only give you huge different numbers. Okay, so you cannot too rely on this number. Okay, so now I introduce this so-called the CFC warming model. Okay, that's has been presented in my publications. Okay, this CFC warming model basically is built on the quantum physics of the Earth's black body radiation. We can use the Planck, the quantum physics of the black body radiation to consider the thermal radiation from the Earth. So essentially, the Earth absorbs the solar radiation heat, right? And then because our surface temperature is 288 Kelvin, near 380 Kelvin. So on the daytime, on the nighttime, the Earth will emit radiation into the space. And because the temperature is 288 Kelvin, so based on the black body radiation, and we can know that the Earth will emit the infrared radiation, and that's different from the visible radiation from the solar, because the solar intensity and the temperature is about 5,800 Kelvin, and they have the invisible spectral range, right? So based on the physics, the Weir displacement law, you can know that the radiation emitted from the surface is infrared. So here we get this red curve. That's based on the quantum physics the Planck formula, it will give you the radiation intensity spectrum. Okay, so you can see that the peak is about 8 to 13 micrometer. Okay, in many literature, you can see they try to present that this black body radiation spectrum peak at the CO2 peak is 15 micrometer. I would say that's misleading. Okay, because you can know that the solar temperature approximately is 5,800 Kelvin. Okay, it's about 6,000 Kelvin approximately. And we know we can measure the solar spectrum. Okay, we have the visible light, right? Approximately is 500 nanometer, the peak position. So you just simple use the physics calculation, okay, and you will know because our surface temperature is 288 Kelvin. So you just base simple Weir displacement law, you can calculate that the Earth's surface radiation spectrum must be peak approximately 10 micrometer instead of 15 micrometer. Okay, so I already discussed that one of my 2010 paper. Okay, if you are interested, people can see that paper. Okay. Also, this is the atmospheric transmittance spectrum. Okay, so here you can see the green curve and the black solid curve, and also the black dot curve. The dot curve, okay, that is measured on the ground using the sun as the black body radiation source. Okay, the green curve is simulated. So basically, you can see that because I have the high concentration CO2 and N2O methane, that's completely saturated. It's completely opaque, right? Non-transparent. By contrast, in the spectral window 8 to 13 micrometer, so you can see that the transmittance approximately equal to 1, and that means it's very transparent, right? Here you have the major peak. That's oxygen, ozone, right? Ozone. Okay. Unfortunately, halogen greenhouse gas, especially CFC, have strong infrared absorption band in this spectral range. Okay. So they highly affect greenhouse gas. Okay. Usually we call this spectral range 8 to 13 micrometer. We call this atmospheric window for two reasons. One, as you can see, that this layer on the peak for this black body radiation from the Earth's surface, right? Another reason is because this spectral range, the atmosphere, essentially is transparent. Okay, so majority radiation energy from the surface is emitted into space through this window. Okay, 8 to 30 micrometer. So this majority radiation will emit into space in this window. So any gas have strong absorption band in this range, the window, okay, will be highly effect of greenhouse gas. If you consider the per molecule basis, then the greenhouse effect of per CFC molecule will million times of the greenhouse effect of per CO2. Okay, and that has been well known. Here, okay, the key issue is that there's some overlap between the Earth absorption band and CO2 and N2O methane. Okay, because of the concentration of water vapor, we know that the water vapor is the primary observer in the atmosphere. Okay, actually, the CO2 absorption only control about 10% of the radiation of energy controlled by water vapor. Okay, so water vapor is a primary observer infrared radiation in the atmosphere, and also the absorption band of CO2 and N2O methane have significant overlap with the absorption band of the water vapor. So in fact, in the 1960s or 1970s, scientists have studied that, especially one Russell team, they already started based on their modeling results, they found that because the dominator of the infrared absorption by water vapor, and because this overlap effect, so when you increase the CO2 concentration, actually the heat radiation in the atmosphere is essentially constant. In other words, the heat radiation in the atmosphere is nearly independent of CO2 concentration. And that has been modeled in the 1960s, 1970s, especially by the Russian the climate model. Okay. This issue is very important and very critical because this associated with this equation earlier I mentioned about that for CO2, the relative forcing, you have this 5.3 times log in CC0. And that's based on the argument that they consider that the central peak at 15 micrometer, that corresponds to 666 centimeter per centimeter wave number. Okay, in this central peak, usually there's no argument that's been completely saturated. But then they argue that in the wind, okay, absorption wind is not yet completely saturated, and that gives you this linear dependence, this log-in dependence. So this absorption. But if this is really true or not, okay, that must be tested by observation. Okay, so therefore, in the latest slide, I will show you the key observation to test that. Okay, so here let me continue my CFC model. Okay, so I start from the very beginning, the initial definition of radial forcing. Basically, when you increase the greenhouse gas in the atmosphere, they will trap the infrared radiation from the surface. So because the trapping of the heat in the atmosphere, so you detect from the top of atmosphere, actually the outgoing long wave radiation intensity will be decreased, right? Because the trapping in the atmosphere. But eventually, the Earth system will reach the new equilibrium. And therefore, to reach the new equilibrium, the surface temperature must be raised up to increase outgoing long wave radiation. So eventually, they can reach the equilibrium at the top of the atmosphere. So based on that classical understanding of the basic principle of world movement, you can write this force as this. Tau, that is the wavelength dependent transmittance, right? And this B is the radiation energy spectrum based on the Planck-Bragg radiation formula. Okay, so you can write this. Now we can make an approximation because earlier shows that the majority of the surface radiation emitted into the space is through that atmospheric window, 8 to 13 micrometer, right? And also because only greenhouse gas in that window are sensitive to make the change for radiation heat in the atmosphere, right? Because that region is very transparent. So when the concentration changes there, they can make the significant change for the heat radiation in the atmosphere. So with that two consideration, then we can make this approximation that now we can write this, the radiation flux from the surface change, okay, just times this transmittance in the atmospheric window, okay, instead of the whole spectrum. We just consider that atmospheric window approximately, okay. And then we can calculate this, the climate sensitivity alpha, just based on the transmittance in the atmospheric window. And this can be measured by satellite based on the spectrum I showed in last slide from the satellite measurement. Then we can find that the climate sensitivity factor for greenhouse gas in this spectral window, that's the hydrogen gas and also ozone molecule. So we get that this is 1.16 Kelvin per watt square meter. Okay. Then we determine this, the climate sensitivity based on this, the quantum physics, and plus this satellite measure the outgoing long wave spectrum. Okay, we get this transmittance. So we found that this, the climate sensitivity factor alpha equal to 1.16 for hydrogen gas. This also the number about it for ozone, because the ozone have observation spectral band in that windows, right? And then we have to determine the amplification factor beta. So again, I use the observation approach to determine this beta value. Okay. We use this where observer temperature change during the solar cycle, 11 solar cycle. Because during 11-year solar cycle, the radiative force from the solar radiation change, okay, can be easy to calculate, reliably to calculate. You can calculate the radiative force, okay, because the change in calm solar radiation. You can have these simple equations, okay. And from this, then you can also write this the direct so-called Planck response, the temperature change, directly response to the change in calm solar radiation energy. So we have this simple relationship. And then we can write this, the solar climate sensitivity factor by this. We already know the surface temperature about 288 Kelvin. And we also know that during solar cycle, the solar energy change, okay, approximately is only 0.1%. Okay, the total solar irradiation change is 0.1%, and on the average is 1361 watts per square meter. So with those well observed determined values, we can find that the temperature change directly response to the solar forcing during solar cycle is equal to 0.072 Kelvin. Okay, and we can also calculate this alpha S is 0.3 Kelvin per watts per square meter. Another observation is that we only well know that during solar cycles, the surface equilibrium global average surface temperature increase approximately is 0.11 Kelvin. Okay, and the lag time, response time actually quite short, only about 1 month to the solar force, because you can trace that the solar intensity change and trace the surface temperature. Okay, actually lag time only about 1 month, so the response is very rapid. Okay, and the temperature fluctuation is only about 0.11. So from this, then we can reliably directly determine that the total feedback amplification factor beta is equal to 1.53. Okay, so here you can see that we determine this beta number by observation. Okay, directly measurement, we determine this 1.53. Okay, and this feedback including everything, including the water vapor, the elevator factor, everything. Okay, the total amplification factor, because you based on this temperature measurement, the observation. So we did that, then we can determine that the solar equilibrium climate sensitivity lambda for solar, okay, equal to 0.46. Okay, and then we can determine that the equilibrium climate sensitivity factor for hydrogen gas or for ozone is equal to 1.77 Kelvin watts per square meter. Okay, so we already determined this value based on this the quantum physics of black body radiation Earth, and also based on this the observation during solar cycle, the temperature change, right? So we determine this, completely determine this the climate sensitivity factor lambda. Okay, so now we can calculate the surface temperature, because the change of the hydrogen greenhouse gas concentration and the change in the solar intensity during the solar cycles, right? And then we can find the surface temperature. Okay. This radial force, we already, for hydrogen gas, I already earlier equation, okay, can directly calculate simple by the linear dependence. And for solar, this can also calculate by the equation given in last slide. So then we can give the parameter-free, no parameter calculation of the global mean surface temperature. Okay, so we don't need to use any adjustable parameters. So this has been given in detail in my book published in 2015. Okay, so now I want to talk to you to share with you the recent progress reported in these two papers, especially for the observation. Okay, I presented the 6 key observations to assess that major substance in the GCM, the CO2 greenhouse effect. So the first key observation is the temperature climatology, okay, in the troposphere and the stratosphere. Okay, so you can look from the ground to about 30 or 50 km. And very interesting, you can see that the warming pattern in the atmosphere actually closely resembles, extremely similar to the space pattern of CFC distribution in the atmosphere. It's almost, perfect match. Another key point is, earlier we mentioned that we have to test the Loria Manapis GCM model. They predict that when CO2 concentration increase, they can see the near surface warming and the stratospheric cooling, right? We already have the satellite data since earlier 2000. We have very good high quality satellite data now, since from 2002. So we look at it, and we also have the wear measurement of CO2, right? We already know the CO2 concentrations keep increase. The growth in rate is larger than ever, right? In the past 2 decades, okay, have the largest growth rate. So if you look at it in the 2000s, the decades average, okay, 2010s minus 2000s, the decades difference. And you can find that actually the temperature in the upper stratosphere, actually they are warming, is increased instead of cooling, right? But we are well known that the CO2 concentration is increased. So this just opposite to this GCM model prediction, just opposite. They predict this cooling, but we observe this warming. I'm not only person to show that actually there are also the bigger research team. They published a paper in 2018, and they found that the temperature in the lower stratosphere also reversed from warming before 2000s, now from the cooling to warming after 2000s. Okay, so this consistent with my observation shows here. Actually, now we see the stratospheric warming instead of cooling, but we see the CO2 concentration increase. So obviously, this just opposite to what predicted by this GCM. Right? So this is the critical observation. Right? Another very important observation is the signature from the major outgoing long-wave radiation. Fortunately, we have 2 satellites. One is in 1970, and then we have another satellite in 1997. Because we have the rapid warming from 1970 to about 2000s, we have that 0.6 degree increase, right? Very obviously. That is the rapid warming period in the record in the past 150 years, right? So based on the CO2 climate model, they will predict that there's a heat trapped by CO2 concentration increase. So you will see the negative band, okay, in the outgoing long-wave radiation. Okay, if you measure on the top of the atmosphere, and you see this negative band correspond to CO2 absorption band in the atmosphere. Okay, and there's a paper published in 2001 by Harris in Nature, and in that paper they shows very good agreement between the CO2 model and the observation. But then the other 2 teams, they make this analysis, the same data set, and they found it very different. Actually, James Anderson at Harvard, he made the analysis. I believe that he had the manuscript in 2002. Okay, and they shows that they didn't see that band predict by CO2 model. They shows almost 0, so that is disappear in the observation. And then the UK team, okay, they also doing analysis the same data set. And again, the results shows here, they didn't see that negative band for CO2 absorption that has been assuming in the climate model. And then Harris's team doing the analysis, and they presented results essentially consistent with the other 2 teams. They didn't see that model predict that negative band for the CO2 at the red curve here. Okay, this is very important. Actually, this is the fingerprint to show that no CO2 rated forcing during 70 to about 2000s. Okay, because we see the drastic 0.6 degree increase in this period of time. Actually, there's no CO2 forcing observed in this satellite. So I believe this is also one very important observation. Earlier I mentioned that for Antarctica, okay, we can also test that GCM prediction at 7 to 10 degree increase, right? And I showed the data from IPCC report because there's free of air pollution over South Pole region, Antarctica. So there's the aerosol level is flat up to now from 1750 or 1850. It's no air pollution there. So you don't have that ozone changer in the lower atmosphere. Of course, in the upper atmosphere, you have the ozone hole there, right? So you have the ozone concentration changer. That's well measured since 1957 over South Pole. This well documented. Okay. But you don't have that air pollution issue. So basically, the temperature there should be covered by the greenhouse gas and ozone. And we also well known that before 1950, actually the ozone changer the ozone depletion have not yet started because that time the CFC concentration have not yet emitted into atmosphere, right? So basically, from 1850 to 1950, there's just CO2 there. Like there's no significant CFC, and there's no significant ozone depletion, and there's no significant air pollution. Right? So only CO2 there. So it's like the well-controlled laboratory experiments to look at Antarctica temperature change because you have CO2 there and you have direct measurement. Actually, before 1958, the only measurement size in the Earth is Antarctica. So you see that the CO2 concentration measurement before 1958 start in Hawaii, okay, actually came from the ice core measurement over Antarctica. So you can see that the CO2 is increased, right, from 1850 to 1950, obviously, right, from 285 to about 315 ppm. And you look at the temperature, actually, there's no increase, even there's slightly decrease, right? So if you make the analysis correlation, the temperature over Antarctica and plot against the CO2 concentration, and you can see that sort of negative trend, okay, minus 0.6 from 1850 to 1950, over 100 years. There's negative correlation. Okay. And then from 70 to 2020, because we know with the CFC emitted into the atmosphere. So this is the CFC concentration, and this the black dot, the square, that is the global mean surface temperature. Okay, the red one is I collect by removing the ENSO, the volcanic effect, okay, nature effect. But their difference is very small between the black square and the red one after making the correction to remove nature effect. Okay, so from the 1970s, and you can see that this temperature change close follow the change of the hydrogen greenhouse gas concentration. Okay, if you make the correlation analysis, you can see the surface temperature change as function as the CFC concentration, and you can see almost a perfect linear dependence, right? So this proves that earlier when we calculate the radiative force of hydrogen gas, you have that linear dependence. So this get well conforming, right? So here, the observation confirms that indeed you can have the linear dependence between the radiative force and the hydrogen greenhouse gas, the linear dependence. Some people might argue that since 2015, the temperature increased again. So here, okay. And this, of course, is important issue we have to start. So in my 2012 paper, actually, I show that, okay, if you look at this temperature change, the global map, okay, look at this after 2000s And with that to 1950, 75, you can see the significant warming over the northern hemisphere, okay, and especially in the high latitude region, okay. And if you look at the difference in the 2010s with respect to 20s, the decades averaging, and you can see that actually the warming is mainly occur in the North Russia and Alaska, right? So in the coastal region, there's warming, okay. You can also look at the sea ice extent change. In the northern hemisphere, you can see that since 1980s, there's significant ice melting, right? And the southern hemisphere is very different, actually quite robust. Even there's slightly increased trend in the sea ice extent up to 2015. And this is for the southern hemisphere. Then since 2015, the start ice melting. Mainly, this can be explained by the decoupling ozone depletion, because ozone itself also greenhouse gas. So when the ozone decouple, the concentration increase. This can be explained by that, can attribute to this the ozone change. Okay, but it's clear that before 2015, the sea ice extent over the southern hemisphere does not decrease, even had slightly increased trend. Okay. So actually, this temperature increase can be well explained this by so-called Arctic amplification mechanism because of the sea ice loss. Basically, you can consider the sea ice as a mirror, and they will reflect the radiation from the sunlight back into space, and that will not be observed. That part of energy will not be observed by the Earth. Therefore, that part will not cause the warming. So when you have the more sea ice, there's more energy reflect back into space. When there's less ice, there's more energy will trap by the Earth and then cause the warming. Right? So this can well explain why we see that suddenly temperature increase again up to 2015. Okay. Actually, this can be proved further. If you look at the temperature change in different seasons, okay, and you can find that actually the up to 2015 warming mainly occur in the cold weather season, in December to February, or in the winter, or in spring. And this didn't occur in the summer and also the fall, right? And this is also consistent with that so-called sea ice loss warming amplification. So this can well explain that why we see the temperature rise again up to 2015. Okay. Actually, you can look at more detail, even look at the different size in Russia. If you look at inland Russia, you can see the temperature is flat. And you look at the coastal area with the ice melting, you can see the temperature is rising sharply. Okay, so this can also confirm that why we see that temperature increase again up to 2015. It's very clear to see that. Okay. This same as slide I showed last slide is get averaged for inland state of Russia, and this the coastal state have the ice melting. Okay. Therefore, when I want to analyze the temperature over ectotropic from 30 degree north to 90 degree latitude north, and excluding Russia and Alaska, the ice melting country or the state. Okay. So now if you exclude these two areas, okay, and you see the temperature, the land surface temperature from 2000 to 2022, you can see almost flat. That increased rate is only 5 millikelvin per year. This is almost flat. Okay. This right side is North America temperature, including Canada, and contiguous USA, not including Alaska and Hawaii and Greenland. And you look at that, even temperature slightly declining trend since 2005. It's minus 8 millikelvin per year, slight declining trend. Okay, consistent. You look at this, the snow cover extent over northern hemisphere, and you can see since 2005 there's increased trend. The snow cover. North America, consistent, also increased trend. Okay, so you can see the global warming has stopped in the North America and this indicated by the temperature and also the snow cap, and also including the temperature from 30 degrees north, 90 degrees north, if you excluded Russia and Alaska. Okay, so in other words, without that sea ice loss Arctic amplification, actually we should observe that the global warming should start to reverse to become the cooling trend or to become the flood without continue warming. Okay. The fifth evidence to test that the CO2 forcing in the GCM. In the late 90s, the GCM also predict that because the CO2 concentration increased, they expect that the significant effect will affect ozone depletion in the stratosphere, and then will affect temperature there. So if we look at the ozone amount or the temperature over stratosphere, and actually that leading to my discovery about tropical ozone hole in 2000 in last year. Okay, so you can see that there's a larger, significant temperature hole here over tropical, and then this hole is associated with the Antarctic ozone hole because, as I just mentioned, that ozone is a greenhouse gas, and ozone also absorbs the solar radiation. So when ozone depletion will make the temperature decrease there, so that we can see this temperature hole associated with Antarctic ozone hole. Here, this temperature hole is very obvious, this associated tropical ozone hole. Okay. I can also use a model, my model, to nicely fit the major temperature or the ozone. Okay. This is global average lower strata temperature for the from 90 degrees south to 90 degrees north, and it can be nicely fit by this equation. In this equation, I only use the halogen molecule concentration, actually ozone depletion molecule, CFC, and I is the cosmic ray intensity. So I don't include in any CO2 concentration here, and I can get a nicely fit with the observable data. Again, this indicates that there's no CO2 climate force on the ozone depletion and the temperature, the climate in the stratosphere. Okay, so that is also opposite to what predicted by GCM. Okay, in earlier this year, I also published one major work about the ozone depletion. So now for the global ozone depletion, actually I come out with this equation. I can calculate the chlorine year that is the logical to make ozone depletion globally. Can be well expressed by this theta is the amount of ozone depleting molecule observed in the atmospheric particle surface. This phi E, that is the electron flux produced by cosmic ray. So you have this concentration, the coverage, and this flux square. Okay, and then I can make a calculation based on this simple equation. I make a calculation the ozone depletion over South Pole, and you can see there's almost perfect agreement with observation, just based on this simple equation. Okay, and again, the mid latitude you can get a good agreement. In the tropical region, you can get a good agreement. Okay, again, here you don't see any CO2 climate effect in this ozone depletion on the global scale. Okay, I don't see any. Okay, because this equation I don't include in any CO2 effect, and the results is excellent, agree with observation in the stratosphere for the ozone depletion. Right? So that is also another strong evidence for no CO2 climate effect. The last key observation is regional surface temperature, and I choose three regions. One is, as we just discussed, the Arctic, and that temperature sharply increased, right? And we already shows that this sharply increase is because sea ice warming amplification. Earlier I showed the strong evidence observation to prove that. Another reason is Central England temperature. Okay, the two reasons I choose that. Once we know that the England is the birthplace for modern industry revolution, right? So the start from England, right? And also because the temperature of Central England, they start from 1859. That is the longest instrument record of temperature in the world. Okay, so they have the longest history. And you look at the temperature, they essentially flat until 1970, and then have increased up to about 2000. After that, the temperature is flat, okay, in the past 2 decades, okay. This is one very important observation, right, for temperature with the longest record in the world, okay. The third one, let's come back to the newest key prediction by GCM, right. They predict that in the latitude, they have 7 to 10 degree increase when CO2 doubling, okay. And we look at this Antarctica, okay, as we showed earlier. This based on the newest version NOAA 5.1 data set, okay. And you can see that the surface temperature over Antarctica are from 1850 to about 1960. It's flat or slightly decreased. They predict we should see the drastic increase over Antarctica, and we didn't see it. And then we suddenly see about 0.27 degree increase between 1960 to 1980 only. After that, from 1980 to 22, essentially flat. And if you look at more detail from 2005 to 2022, actually there's a declining trend, right? So this drastic different from prediction by the GCM, right? By contrast, I can apply my CFC volume model to make a calculation about this temperature change, this 0.7 degree. So based on my model, I can calculate that the greenhouse effect between 1960 to 1980, because of hydrogen greenhouse gas, that will make a 0.31 degree increase. And then we have also weather measurement, the ozone depletion over Antarctica, because the CFC emission into the atmosphere. Based on the major ozone depletion, I can also calculate the radiant force from ozone is equal to minus 0.051 times the parameter gamma here. This gamma is between 0 and 1, and that is to consider the potential saturation, the ozone infrared in the atmospheric window. Earlier we showed that dip peak in the atmospheric window between 8 to 30 micrometer. So if this is 0, it means that it's completely saturated. And if this one just shows the linear dependence, means there's no saturation. So obviously, the realistic number should be between 0 and 1. So based on this, then with my model, I can calculate that the net temperature change during 1960 to 80 is between 0.22 to 0.31 Celsius degree. And the observation is 0.27. So just perfect in the middle of this range given by this model. Okay. Again, here 1.77, the climate sensitivity is not Turing, it's not hidden parameter. This number is well determined from the black body radiation spectrum and from the satellite major transmitting spectrum. Okay. So there's no any Turing parameter, and I get almost perfect agreement with observation. Okay. That's what IPCC AR6 say. Okay. Actually, in page 987, it states that Southern Ocean's sea ice surface temperature has been slow to warm over the ensuing period, with cooling since 1980s. This stands in contrast to the equilibrium warming pattern, either inflow from procyclical or simulated by the modeling, okay, under CO2 forcing. So I agree, this is significant disagreement with the model based on CO2 forcing. Okay. Based on this observation and this GCM prediction, okay, basically I can say that this observation actually allows that the test of CO2 climate model, because the drastic difference, in no way the CO2 climate model can be right, okay, for climate change. Because as earlier I mentioned that Antarctica is the well-controlled laboratory. There's very clean up to 1960. Just CO2 there. There's no significant CFC, and there's no significant ozone depletion before 1950. Right? So in that specific area, it's very clean. Just CO2 there, and you have good measurement of CO2, you have good measurement of aerosol concentration, you have good measurement of ozone, everything there, and you don't see anything, okay? So to me, this observation is very important, and this announced the depth of CO2 climate model. The surface temperature based on this observation and my model calculation just crossed by CFC and ozone depletion since 1960 over South Pole. And because the ozone concentration is controlled by CFC and cosmic ray, therefore, the temperature just controlled by CFC and cosmic ray, okay, based on this calculation and observation. For the nature effect, you can easy to consider ENSO and volcanic aerosol. And this has been well done in the publication in the literature by the empirical model developed by Lin and Lind. Okay, this can be seen from this. Okay, so basically, I just adapt the empirical model developed by two researchers. Okay, so based on that, this is the prediction I made based on by this model. Okay, this observation based on the data set. We should expect that right now we are in the peak for the warming. Okay, in the coming decade, we expect gradually to see the cooling trend. Okay, and that's because the greenhouse effect, CFC, rather than CO2. If CO2, you will predict that. Okay, keep in mind, appear that GCM can also good match with observation, but you have to know that they use just the parameter, multiple just the parameter. In my CFC model, I use 0 parameter. There's no any adjustable value, right? So it's different, okay? And I, based on the last slide, that surface temperature of Antarctica. So I am fully optimistic we will see a gradually cooling trend in most of the time of this century, okay? So that based on what I presented today, this is the conclusion. So the key observation have disproved the CO2 climate model. The fundamental in the GCM arise likely from the improper processing of overlapping effect of water vapor on the climate force of CO2, N2O, and methane. The observation provided a strong inference of the contribution CFC to global warming in the late last century. And that strong indicator that global climate change has been primarily caused by hydrogen greenhouse gas since 1970s. The observation also agree with the CFC warming model, okay? But there are strong contrast to the major conclusion in IPCC AR6 because they still make the major conclusion that CO2 are leading to the warming, okay? So obviously, either the key observation or the model is strongly contrast to that the conclusion of CO2 for global warming. Right? The observation also shows that the reverse and global warming will have occurred since about 2005 if there are no article amplification, because we shows that the warming since 2015 mainly is because the sea ice loss associated with the Antarctic and Arctic amplification. Right? The calculated results by this physical model of hydrogen greenhouse gas with no tunable parameter also shows excellent agreement with observation of the surface temperature, particularly with the surface temperature over Antarctica since 1850. Right? So all of the observed and the calculated results strongly supported that the hydrogen gas played a dominant role in causing the world warming observed in the late last century, essentially between 1970 or 75 to 2000. So all because of CFC plus ozone depletion because CFC and cosmic ray. Okay, so that is my major conclusion. Here I want to talk about briefly about the possible potential ramifications. Okay, so please start model guide adjustment to measure temperature of the ozone data set. Other research reported it, and personally, I also have seen that. I saw either NASA or NOAA or UK, they keep adjusting to the temperature data set. As a researcher, I feel very nervous when I have to use their observation data set. But when I see when they adjust that too frequently, as a researcher, I feel very, very nervous when I have to compare with my model results with their observation data set I have to use, right? Because they are under all major data source. Okay, so hopefully they stop either by GCM or by the chemistry climate model. So to stop this model guided adjustment to this temperature or the ozone data, because the observation must be objective rather than subjective, right? Number two is that there has been a proposal for so-called geoengineering, geoengineering. That is proposed to inject the aerosol particle into the stratosphere, okay, try to reduce the global warming. And in my opinion, this must be abundant because they will increase ozone depletion and will also cause other harmful environmental effects. And there's no point to do that because based on the observation in my model results, the climate change has been merely controlled by CFC. So if we control CFC, we should be optimistic to see the temperature will gradually return to before 1970s, right? So there's no point there because they will also create the harmful effect, environmental effect. Okay. The last one is that recently the review have shown that point out that the entire project of parameterization, okay, that means there were discovery of these parsimonious presentation through mathematical method, okay, that have no future for GCM. They already point out that. But they also propose for the new generation of GCM, try to make them can match better with observation series of models through substantial increase either the resolution or to introduce the more details, or through use the so-called machine learning techniques. Okay, in my opinion, those methods, those efforts, eventually might be just a feature, okay, attempt, okay, useless, because if the essential assumption in the GCM based on the accepted huge radial force, there are no physical foundation, they have no observation support. Then if the major assumption is incorrect, then whatever how you introduce the new details or use the new machine learning techniques, it will not make it a bigger change. Because if the foundation is not right, there's no possibility you can get the right prediction. Okay, so that is my personal opinion. Okay. So finally, I acknowledge that my research partially supported by the answer fund. Okay. So thank you.
You mentioned offline that you have had email correspondence with Will Happer and Richard Lindzen. I'm just curious if there's anything you can share about what they think about this and about the prospect of mild cooling between now and 2100.
Yeah, I did have some email correspondence with these two excellent researchers. They have concern about the reliability of the data set, observation data set, because probably they also pay attention to the frequent adjustment to the data. So one of the researchers expressed to me they have serious concern about the reliability of observation data set, such as from NASA or from NOAA. They have big concern about that. And I already point out in the last slide, right? I share that concern. Obviously, we have the different understanding, different opinion about that. But I think that exactly is what the Dr. Eber point out, right? Science is controvertible, is disputable. And I'm enjoying my discussion with either Dr. Lindzen or Dr. Howard because we can have different opinion and we can discuss. And that is exactly we needed it.
Very good. When you talk about model-guided adjustments to measure temperature data, have you followed the work of Tony Heller at all to look at past adjustments, or is it related, I wonder, in any way? Are they adjusting data from the 1930s using models? Are they doing that now?
As a researcher, because in the past decade, of course, I download several versions from that. like NOAA or the UK, right? And when you compare a version, they change all the time. That's something make me very nervous. Even I'm not exactly follow that, but I do in my computer, I do have several versions around that, right? Including that the Central England data. That data have the longest historical record, right? And they didn't change it probably until about 1 year, about 2 years ago. They keep it there very consistent. But in the past 1 year, they make a 2 adjustment. And each time they increase a little bit, okay, just very tiny, okay. To be honest, I always say that in my 2022 paper, I tend to use the older, as little adjustment as possible. I try to use as original as possible data set. I will prefer to use either, UK, the version 3.0 or 4.0. I'm nervous when I use 5.0 because I know they make a several adjustment based on the data I get from there. And something is difficult, then they discontinue to provide the original version data, even the Central England data. And they stop there. Now they just keep the new version, I think, from this year.
Yeah, I just was talking to the Connollys and Willie Soon on this podcast, and they were talking about having to download the data sets every day because there were adjustments.
I don't do that. I didn't do that way because I'm busy, okay? But I do have several versions. And each time I see the change, okay? To be honest, I'm nervous, right? Because I want to get the objective, original data. And if you keep a changing, sometimes I'm not sure, okay? I'm not sure. And that same thing happened even to ozone data I've seen before.
Very good. All right. I won't keep you too long, but any other points you want to make here before we go ahead and wrap this one up?
Yeah. Firstly, I think that real science is disputable, is controvertible, okay? And I think that if we face objective with the data we have seen, we're still able to make a clear conclusion about what is the real cause of the climate change. If we don't consider politics, we don't consider, the other fact. If we just based on the scientific reason, based on the scientific observation, I believe we should be able to make a very solid conclusion about climate change, the main cause of climate change. And based on the data I have seen, or the calculation I've done, I'm quite sure it is because of CFC, not because of CO2.
All right. Thank you very much. I really enjoyed your presentation. Thanks for all your work and your independent thought. This is great stuff. So
thank you.
Qing-Bin Lu. We'll see you next time. Thank you very much. Goodbye.
Thank you. Bye now.